Welcome to the module Optimizing Motion. Optimization is a process of defining the best design with respect to defined constraints and goals. In this module, you will learn how SolidWorks Motion can be used to optimize a design. For a better understanding of motion optimization, we will conduct an optimization study on a medical exam chair. In this module, you will learn how to define sensors to monitor the results of a motion study. You will also learn to create a design study, define parameters and variables in a design study. You will also learn how to optimize the features of a motion study. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. Medical examination chairs found in most clinics and hospitals have to be sturdy, easy to use, and aesthetically pleasing. The chairs have to comply with certain medical standards and offer maximum comfort to the patient. The height and tilt adjustments should be easy to operate for the medical staff. Due to space limitations and power requirements, the overall size of the chair has to be small and the individual components should be lightweight. In this module, we will perform an optimization study to size the actuator mounted on a medical examination chair. The medical examination chair needs to have a certain range of travel, but at the same time, we have to limit the size of the actuator to raise or lower the chair. The travel of the chair is between 0.3 meters and 0.6 meters. The dimensions of the components that form the lifting mechanism are variable within a certain limit. In the optimization study, these dimensions are the design variables. The maximum and minimum height of the chair are the constraints monitored by motion data sensors, and the goal is to minimize the actuator force, also monitored by a sensor. The following steps will be followed in order to perform an optimization study on the chair. Create a motion study. Add a linear motor. Add gravity. Define contact. Calculate the motion. Plot the results. Create a design study and define parameters. Post-process the results. Let's see how to disable mates, create a motion study, and solve it. Click Show Me to launch a demonstration video. The assembly file medical chair has been opened. Click Tools and click Add-ins. Make sure that the add-ins for motion and simulation are checked. Click OK. Verify that the document unit is set to meters, kilograms, seconds. Create a new motion study entitled Chair Motion. Set the type of study to Motion Analysis. Next, we will set the simulation time. Right-click Key Properties. Click Edit Key Point Time. Set the simulation time to 4.1 seconds and click OK. Mates can be suppressed or unsuppressed within the timeline. This can add or remove stability in a motion analysis. In this case, a mate is currently keeping the chair from articulating up and down. We will keep this mate suppressed until 0.1 seconds and then unsuppress the mate, allowing the linear actuator to move the chair. The timeline has been zoomed in. Expand the Mates folder in the Motion Study tree. Click Co-Incident 12. Right-click in the timeline at 0.1 seconds and click Suppress. This creates a key that suppresses the mate at 0.1 seconds so that it will have no effect after this time. Now, we will create a motor that drives the piston. Click Motor. Under Motor Type, click Linear Motor. For motor direction, select the cylindrical face of the piston. Click the Component to Move Relative to field. And click the Motor component. For motion type, click the drop-down arrow and click Segments. Retain the default values for value y and independent variable x. Add a row in the table to enter the values by clicking Click to add a row. Before entering values here, we must remember that a mate constrains the chair for the first 0.1 seconds of this simulation. The motor will be unable to move the chair while the mate is active. Therefore, we will specify 0 movement of the motor for the first 0.1 seconds. Retain 0 seconds in Start X column. And enter 0.1 seconds in End X column. Click to view the drop-down list under Segment Type. And set Segment Type to Linear Default. Similarly, add a second and a third row. For the first 0.1 seconds, the motor does not move. It then takes 2 seconds to move the motor up to 0.13 meters and finally 2 seconds to move down. Close the Function Builder dialog. Click OK to save the definition of the motor. Now, we will apply gravity to the assembly. Click Gravity. For gravity parameters, click -y as the direction and click OK. Click Calculate to run the motion study. Here, we can view the raising and lowering of the medical chair. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about creating and solving a motion study. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Sensors monitor the selected properties of parts and assemblies. Sensors can be used in a design study to perform an optimization study or evaluate specific design scenarios. There are different types of sensors such as simulation data, mass properties, dimension, interference detection, measurement, proximity, costing data, and motion data. The motion data sensors can be used to monitor result quantities such as displacements, velocities, accelerations, spring constants, forces, etc. An alert can be set to notify the user when a sensor value deviates from the set limit or reaches a particular maximum or minimum value. Let's see how to add different sensors to the motion study. Click Show Me to launch a demonstration video. In the optimization analysis, two constraints will monitor the height of the chair to ensure that it is able to lift high enough and come down low enough throughout its articulation. These constraints must be monitored through sensors. Before we begin adding sensors, we will first create a plot of linear displacement of couch center component, which is the tray under the center of the chair in the Y direction. Click Results and Plots. Define the plot by displacement, velocity, acceleration, linear displacement, and Y component. For Select 2 Points faces, click the bottom face of the couch center. For the component to define XYZ directions field, click the base frame and then scroll down. Retain the rest of the settings as they are and click OK. Then, rename the plot to Chair Y. Now, we will create a sensor for maximum displacement. Right-click the Sensors folder. Click Add Sensor. Click Rebuild. For sensor type, click the drop-down arrow and click Motion Data. For Motion Study, click the drop-down arrow and click Chair Motion. Under Motion Study result, click the drop-down arrow and click Chair Y. Under Properties, make sure that the criterion is set to Model Max. Alert notifies the user when the sensor value deviates from the specified limits. We will clear this box, otherwise a violated constraint would be displayed automatically in the optimization study. Clear Alert. Click OK. Expand the Sensor folder in the SolidWorks Feature Manager. The Sensor 1 has been renamed as Max Displacement. Similarly, we will create a sensor for minimum displacement. We have created the sensor named Min Displacement for the minimum displacement. The goal of the optimization analysis will be to minimize the force required by the motor while ensuring the chair raises up high enough and comes down low enough. Sensors have already been created to monitor the height of the chair. We will create one more sensor to monitor the force of the motor. We will start by plotting the force required to lift the chair. Click Results and Plots. Under Result, select Forces as the category, Motor Force as the subcategory, and Magnitude as the result component. Under Select Translational Motor Object to create Result, click Linear Motor 1 from the Motion Manager tree. Click OK. Next, we will rename the plot as Motor Force Plot. The required force is a bit over 2,100 newtons. Now, we will add a sensor for maximum force with the sensor type set to motion data, motion study set to chair motion, and motion study result set to motor force plot. We have created the sensor named motor force for the maximum force. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about adding sensors. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. Design studies can be used to analyze an assembly in which the motors, geometry, springs, and dampers, etc. are to be treated as design variables. Results, such as displacements, velocities, and accelerations, can then be graphed as functions of the design variables. A design study is defined in two steps. Step 1, specify parameters. Step 2, specify combinations of the parameters with their numerical values. The optimization analysis is defined by three design study parameters: variables, constraints, and goals. Click each tab to learn more. Design variables define what can be changed in the model. They are defined using parameters. Parameters are quantities which can be varied in the design study to manipulate the behavior of the assembly. Constraints define allowable ranges of displacements, velocities, and other parameters. Both minimum and maximum values can be specified. Constraints narrow down the optimization space. There are two possible outcomes of an optimization study. The first is that the limit of the design variable has been reached. The optimum design then lies on the boundary of this design variable that has reached a limit of its allowed range of variation. The second possible outcome is that the constraint has been reached. The optimum design then lies on the constraint that has reached the limits. Goals are also called the optimization criterion or optimization objective. The goals define the objective of the optimization study. A global variable is a value or a model dimension that can be used in an equation. All global variables in a model are displayed in the Equations folder in the Feature Manager design tree. In an optimization study, a driving global variable can be used as a variable, whereas a driven global variable can be used as a constraint. For more details, please refer to the SolidWorks online help. Let's see how to create a design study. Click Show Me to launch a demonstration video. Now we will create a design study. Click Design Study. Rename the study to Chair Optimization. The Design Study interface opens up at the bottom of the screen. It offers two view styles, a variable view where parameters can be entered in a variable form, and a table view where a discrete set of values for each variable can be shown. In this optimization analysis, we will specify three variables. These three variables will control the lengths of the various linkages under the chair. These lengths are currently controlled by global variables. Now, we will define the variable and its values. In the Variable view, under Variables, click the drop-down arrow and click Add Parameter. The Parameters dialog box is displayed. Under Category, click the drop-down arrow and click Global Variable. Under References, click the drop-down arrow and click Scissor Length equals 0.5 as the global variable. The Value field displays 0.5 automatically, and the Linked field shows the star symbol indicating that it is tied to a model dimension or equation. Enter Scissor Length as the name. Apply the changes and close the dialog. Under Variables, click the drop-down arrow and click Range. Enter the value 0.4 as the minimum of the range. And enter 0.6 as the maximum of the range. Now, we will add a second variable. Under Variables, click the drop-down arrow to add a variable. Click Add Parameter to add a second parameter. With scissor height as the name, global variable as the category, and 0.2 as the value. Apply the changes and close the dialog. Under Variables, click the drop-down arrow corresponding to the variable scissor height and click Range. Enter the value 0.15 as the minimum of the range and retain 0.3 as the maximum of the range. Now, we will add the last variable with piston offset as the name, global variable as the category, and 0.5 as the value. Under Variables, click the drop-down arrow corresponding to the variable piston offset Click Range. Enter the value 0.5 as the minimum of the range, and enter 0.7 as the maximum of the range. This completes the definition of the variables in the design study. Now we will define the constraints. Remember, constraints are monitored through sensors. In this case, the constraints will ensure that the chair can lift up high enough and come down low enough. Under Constraints, click the drop-down arrow to add a constraint, and click Min Displacement as the first constraint. Click the drop-down arrow corresponding to the constraint Min Displacement. Click Is Less Than, and enter 0.375 as the maximum value. Now, we will define Max Displacement as the second constraint. Under Constraints, click the drop-down arrow to add a constraint. Click Max Displacement. Make sure Is Greater Than is selected corresponding to the constraint Max Displacement. Enter 0.6 as the minimum value. The reference study is automatically set to chair motion for both the constraints. This completes the definition of the constraints in the design study. Now, we will define the goals. In this case, the goal of our study is to minimize the amount of force the motor will exert. A sensor has already been created to monitor this value. Under Goals, click the drop-down arrow to add a goal, and then click Motor Force, and retain Minimize as the objective. Again, the reference study is automatically set to chair motion. Click Design Study Options. There are two solving methods available for optimization studies. Effectively, there is an algorithm that takes longer because it is more precise. This is the high-quality method. There is also an algorithm that is faster but is less precise. This is the fast results method. The fast results algorithm uses a different interpolation method when optimizing. It is suggested to start with the fast results method and then move on to the high-quality method in practice. More information can be found in the help documentation under Design Study Outcomes. We will perform this analysis using the high-quality method. Make sure that Design Study Quality is set to high quality. Click OK. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about creating a design study. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Let's see how to optimize the design study. Click Show Me to launch a demonstration video. Make sure that the optimization box is checked. Let's run the design study. Click Run. The Results View tab is activated, and the global results are shown in the Design Study dialog box when the study completes. The design study took 15 steps to reach a converged solution. The value for each variable, constraint, and the goal can be seen for a particular iteration. The green column indicates the optimal design, whereas the red columns indicate that the iteration did not satisfy all the design constraints. In the optimal design, the length of the scissor has decreased from 0.5 meters to a little over 0.4 meters. The height of the scissor has increased from 0.2 meters to just under 0.23 meters, and the piston offset has increased from 0.5 meters to just under 0.7 meters. Now, we will examine the optimized results. The result of each iteration can be visualized by clicking on that column. Click the optimal column. The reference motion study is updated to reflect the optimal design. Click the Chair Motion Study tab. The motor force plot is displayed. The required force has decreased from 2,106 newtons to 1,467 newtons, a reduction of approximately 30%. Before proceeding, note that the SolidWorks model geometry has changed. For this reason, optimization analysis should never be conducted on production part files. An optimization analysis should be conducted using local copies of parts or assemblies. Now, click Save. And click Save All. Finally, click Close to close the file. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about optimizing a design study. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. You've reached the end of the module, Optimizing Motion. Here are the key takeaways from the module. Click each tab to learn more.